Okay, let's actually make this one step more sophisticated by actually incorporating the chain rule into this. So remember that essentially without the chain rule, the integral of x to the n dx is, and we do the add 1 to the exponent, divide by the new exponent, and then don't forget to add the plus c. Well, if instead of thinking of our variable as just a plain old x, what if we thought of it as u, where u is like some secret formula of x's? So essentially we just replace the x's with u's, and you're like, okay, well, what's the big deal? Why does this make a difference? Well, now the du actually means something, right? So it's the derivative of whatever formula you had underneath this exponent. So the du here means the derivative of this thing. And notice that even though there's a du here, there's no du over on this side. So it's as if the du kind of goes away. So, and that's not surprising, because when we did the chain rule in the forwards direction, the derivative just sort of appeared. So in this case, you have to sort of start with the derivative as part of your integrand, and then it goes away. So let's sort of see what this would look like in practice. So let's just say we have the indefinite integral of x to the 5th plus x cubed to the 10th times 5x to the 4th plus 3x squared dx. Now, this looks horrible. It's like, oh my god, there's all this different stuff right here. But actually, it's not that bad. Because if you look at what we have here, so you've got a formula being raised to a power. So this is like your u. Here's your n is 10. And this horrible mess afterwards, all of this is our du. Because notice that if you take the derivative of x to the 5th plus x cubed, so this is our u, so if we find what du is, the derivative of x to the 5th plus x cubed is 5x to the 4th plus 3x squared. So if we want to take the derivative, we've got our du here, which is what we need, and it's just about to go away. So the answer says, whenever you have a formula raised to a power, as long as the derivative is after it, when you take the antiderivative, it's just the original formula, u, you add 1 to the exponent, divide by the new exponent, and add that on. So x to the 5th plus x cubed to the 11th power, all divided by 11th, and then you add the plus c. Let's actually do a quick double check to see that the answer we just got for our antiderivative is actually correct. So one way you can check to see that our antiderivative is correct is by taking the derivative. Because don't forget what our claim is. So when we say this indefinite integral, or antiderivative, of this equals this, what we're actually saying is, if you take the derivative of this, what we're claiming is the antiderivative, you should get back to this, right? Because we're saying that this is the antiderivative for this. So, alright, let's go ahead and check it out. So let's actually verify that our antiderivative is correct by taking the derivative of it. So if we take the derivative of x to the 5th plus x cubed to the 11th over 11 plus c, well, we fall off the cliff, and that brings this 11 out in front this 11 out in front right here. Then we have to lose a life, so it becomes a 10. But then, by the chain rule, don't forget, we have to multiply, so we're using chain rule in the forwards direction now, the derivative of the inside goes on the outside. So the 11s are going to cancel, and we're left with exactly what the original problem was. So, in fact, this is correct. This is an antiderivative of the original problem. Alright, let's try something with some trig. So, again, we know from the fundamental theorem of calculus, we do the integral of cosine u du, notice these are u's, not x's, so formulas of x's, is the sine of that u plus c. And again, it's really important to notice here that the u is a formula of x's, and in order to be able to use this shortcut, you need to have the derivative of what's inside the cosine on the outside inside this integral to be able to use this shortcut. So, just to do an example, suppose we asked, what's the integral of cosine x squared x dx? So, do we have what we need? Well, almost, but not quite. Because we've got, oops, sorry, I lost my pointer. So, we've got the cosine of a formula, but if we want to use this shortcut, it says you need the derivative of what's inside the cosine to be outside the cosine. Well, what's the derivative of x squared? Well, outside here we've got x, but what we really want is a 2x. So we're missing a 2. Well, we do what I call the wishing game. So we just go ahead, you can do this as long as you're missing a constant for coefficient. You just put the 2 there. But that's, of course, changed the problem. So to balance it off, we have to write a 1/2 on the outside. So now, in fact, we haven't changed the problem, because 1/2 times 2 is just 1. So this part in orange, with this one little black 2 here, now exactly fits the template of what we have. So in this case, the u is x squared. The du is the 2x. So our answer is just going to be, so we still have the 1/2 from the outside there, so this 1/2 is still there. That's the 1/2 we need to create ourselves when we put this 2 on here. So we've got 1/2 times the sign of the original formula, the thing inside the cosine, which was x squared. And then don't forget we have to add on the plus c. Now, one little trick that people do in mathematics a lot is if you distribute this 1/2, you're going to get 1/2 sine x squared plus 1/2 times c. But don't forget what c represents. C represents any constant at all. So if you do 1/2 times any constant, well, that's still any constant. So we can just give that a name. We can call it capital D. So we can say that's 1/2 times the sine of x squared plus d. But mathematicians get really lazy because it's traditional to use plus c for any constant. So rather than calling it d, we just go ahead and call it plus c. So in practice, what people do is they say, all right, I do 1/2 times c. Well, what's 1/2 times c? It's 1/2 times any constant, which is still any constant. So we just still go ahead and call it c. So rather than writing 1/2 c and giving it a new name, we just keep writing c. So what I think of it as c is like a cannibal. So if you do 1/2 times c, it stays c. The c eats the 1/2. In fact, the same thing happens if you were adding it, right? If you do 1/2 plus c, that's just 1/2 plus any constant, which is still any constant. So it's still just c. So adding or multiplying or subtracting or dividing anything with the c just eats that number in front as long as it's a constant, and it becomes c. So one last thing I should mention is that there's actually an alternative way to have done this problem. So rather than using the wishing game, where you say, oh, I really wish that there had been a 2x there, so I put the 2 there and put a 1/2 on the outside, there's a way to sort of automatically make that happen, which for this particular problem probably really wasn't necessary, but let me just go ahead and show you that way, and it's to do something called u substitution. So if you've got the problem, the integral of cosine x squared x dx, one way to sort of think about it is just imagine that we've got, all right, the cosine of a formula here. So whatever that formula is, you just give it a name, and we'll call it u. So you just write on the side, and it's really important to write this out. Don't assume the reader knows what you're talking about. So when you write u equals x squared, well, if u equals x squared, then that means x is equal to u to the 1/2 power. And then you can go ahead and take the derivative. So if x equals u to the 1/2, then dx, that's the derivative of x, is 1/2 u to the negative 1/2 power. I'm using the power rule here, but now don't forget by the chain rule, you have to multiply by the derivative inside. So at this stage, we're now going to go back to the original problem and replace all the x's with u's. So let's see what we have here. So instead of cosine of x squared, we know that x squared is really u, so we got the integral of cosine u. And then we also have that x, so that x is now u to the 1/2. So here, remember, x is u to the 1/2, so I replace this x with u to the 1/2. But then we also have the dx here. This is the thing that students often forget. They go, oh, well, dx, I'll just write du instead. But dx is actually 1/2 u to the negative 1/2 du. So when you replace the dx, you got to write all of this right here. So that's where all of this came from. So cosine u to the 1/2 times 1/2 u to the negative 1/2 du, which sounds horrible, but actually there's some nice cancellation that happens. The u to the 1/2 and the u to the negative 1/2, they cancel each other out. Right? You can think of it as 1/2 plus the negative 1/2 is 0, u to the 0 is 1. And then we can also take that 1/2 and just pull it outside the integral sign. So in the end, what you're just left with is 1/2 the integral of cosine u du. And we know what the integral of cosine u du is. That's exactly in the template that we had it for the backwards chain rule before. It's just 1/2 sine u plus c. Now, the one catch to this, though, is we're actually not allowed to leave it saying sine u, because u is something we just made up for this problem. We can't have u's in the answer, because the original question was all x's. So that means our final answer has to all be in x's. But again, no problem. So we know that u is equal to x squared. So we just go ahead and write 1/2 sine of x squared plus c. And this is just a different way of doing that exact same problem. This is called u substitution, as opposed to playing the wishing game, where you just wish the 2 was there, write a 1/2 on the outside, which I think was actually much easier for this particular problem, but you can use either way you want. Well, good luck in fighting the Bobs in class on Monday.